do is we can set a group, right? So actually, the first little bit of that instructional video, I think we've got down. So we've got a group. We can define the trivial representation, just following what you set out, and get an idea of what the roots are.
Hold on a second, Paul. I hear a lot of white noise. Do you hear that?
No, I think it's okay on our end. Is that better?
A little bit. Are you using an external mic?
I am, yeah.
Just try moving it around a little bit. Let me see if that's the issue.
Okay. How's this? Better or worse?
Seems the same. It's okay. Fine. Okay, go ahead.
Okay, so yeah, basically we can do the stuff that you've got in that getting started with Relax video up on the website. Beyond that, we don't know anything.
Okay.
And what the main thing I'm interested in knowing is how to interpret the output that we get from these things.
Right.
So, yeah, maybe we could start off with SL2. Is that all right?
Sure, of course. SL2 is a great group.
Okay. There we go.
Okay, so I will type, and you can stop me. So, well, let's see. I've launched the programs. You say you know how to do that, and
yeah.
I always load this my script, which has tons of stuff in it.
Okay, that's where we are too.
All right, and then so the first thing I'll just mention a few things before we start. So, actually, I'm gonna now that I've done this, I realize I've already gone too far. I'm going to quit and start over. Before you load anything, I recommend you. My favorite command is tab.
Tab.
Hit tab twice, and it says you see there. It says display all 204 possibilities.
Okay.
Do you see that? Do you see that on your screen?
I do. I see it.
Yeah. Okay. So I hit yes, and this is all of the objects that the software knows about. Most of them are commands, but there are a few variables mixed in here. So in general, command completion is incredibly helpful, and in particular, the tab does command completion on on no string, so it shows you all the possible completions. And you can see all of the possible commands, okay?
Okay, so make sure I understand. This is everything I can get Relax to do for me.
These are all right, this is every single command you can give.
Okay.
And another very useful thing is the command what type. So if you say what type, for example, what's a good example? Let's do what type real form. And you need a question mark at the end. And this is extremely useful. It tells you the format of this command. And for example, here it's saying that the input is a pair, an inner class, and an integer, and the output is a real form. Or in another version, you give it an inner class, a matrix, and a rational vector, and various other possibilities. Okay. So sometimes if you give a command and it complains about it, and you have the wrong format, you can just say what type, and it'll tell you about it. Okay. So now let me load my, and you'll see if you do tab now, you'll see there are 482 possibilities. Now there's tons of stuff that's been loaded, a lot of which is really basic, and you always want to have. But anyway, it's quite a long list at the moment. All right.
Okay.
Okay, so let's set G is equal to SL2R. And let's just check the coordinates. Rho of G, for example, is 1. And
okay, yeah, you can stop right now.
Okay.
Okay, so I see this 1 in square braces divided by 1. What does that mean?
So a vector, I'll just do an example. A vector is an array of integers with square brackets. That's an integer vector.
Okay.
And you see it says bracket int. So the brackets means it's a list, and it's a list of integers.
Okay.
We also need rational vectors, and so that's what this thing with divided by is. So if you set v is equal to 1, whoops, 1, 2, 3, excuse me, divided by 2, it says it's a rat vec.
Okay.
And so it's a vector of rationals, and you can alternatively give it like this. You can say 1 half, 2 halves, 3 halves, or whatever. Whoops, false. Set v is equal to this. It also will show it to you as a list of rationals.
Okay.
Okay. So a lot of stuff in the software is integers because x upper star of t is defined to be zn. There's a basis chosen of x upper star, and every element that's the character lattice of t. Every element of x upper star is given by an integer matrix, and most stuff involves integers. But rho, for example, might not be in x upper star. It might be in the weight lattice and not x upper star. So for that, you need a rational.
Okay, now rho for this guy should be 1 half the root vector.
Yes.
And I don't see a half here. So what basis? I guess this is using the weight lattice.
Let's check what the simple roots of G are. So these are columns, by the way. So in whatever coordinates it's chosen, the simple root is 2.
Okay.
So I mean it's the usual coordinates for SL2, and for classical groups, for example, we've always tried as hard as we can to get the coordinates to be what you're used to. For an arbitrary group, the coordinates can be fairly terrible, and it's not recommended to try and understand them in any decent way. You can find out what roots and things are, but typically the basis that it chooses of x upper star is not guaranteed to be nice in any way.
Okay. So yeah. If it's a nice group like, I don't know, SLN
yes.
or SP2N or something like
yes.
that, I'm guessing that the basis you choose is something I could find in Bourbaki or something like that.
Yes.
Is that okay? All right. Okay.
Now, let's do an example of that. So, for example, if we set G is equal to GL3R, and I do the simple roots of G, they're what you expect. 1 minus 1, 0, and 0, 1 minus 1.
Okay.
Unfortunately, if you do SL3R, that can't be the case because you're familiar with coordinates having 3 entries, but SL3 is ranked 2, so it's not available. So you'll see here, for example, that for SL3 the coordinates are fairly ugly.
Okay, so yeah, I'm having a hard time figuring out what basis for x upper star t you're using in this case.
Beats me. Like I say, I mean, you sort of don't want to know. The point is, the first basis. Yeah. Anyway, what can I say?
Kind of reverse engineer it.
Yeah, you could figure it out. But actually, I think what it is. Let me do one bigger example. If you do G is SL 5R. Yeah, so the first 3 roots are what you expect, and then the last one it sort of wraps around.
Okay. All right.
Okay, but like I said, anyway. So let's go ahead.
So this is not really some sort of canonical choice of basis that Relax uses. It has some sort of algorithm to figure something out, and it may not always look so great. That's
Absolutely.
The bottom line.
Absolutely.
Okay. All right. Well, that's good to know. Okay. So there's some mystery around what the basis for x upper star t is, but Relax knows what it is. And in the case of SL2R, the one we were just looking at, the basis is the weight, the fundamental weight.
Exactly.
Okay.
All right. So let's see. What else would we like to know? So I showed you the simple roots. Let's look at KGB. So this is one of the important underlying objects in the software. So this is a list of K orbits on G mod B.
Okay. K orbits on G mod B. Okay.
Everything complex. So so G mod B is the projective plane.
Yeah.
And K is C cross, and it's acting by multiplication by Z squared. So there are three orbits. There's two closed orbits, 0 and infinity, and there's one open orbit. And in this list, 0 and 1 are the two closed orbits, and 2 is the open orbit.
Okay.
This is indicating that associated to each element here is a Cartan involution, and it is a Cartan really. So these two elements here, 0 and 1, the associated Cartan is the compact Cartan, and the simple root is labeled N, meaning it's imaginary non-compact.
Okay.
And this guy here has to do with the split Cartan, and the simple root there is real.
So I should be thinking about this Cartan involution on the dual group, right?
No.
No?
Nope.
So this is a Cartan involution on SL.
On SL2C.
SL2C, yeah.
Yeah.
Okay.
And I mean, part of the Atlas Yoga is that we fix once and for all a single complex Cartan subgroup H.
Yeah.
And then what we do is we vary the Cartan involution of it. So in the first two cases, the Cartan involution is the identity, meaning that the corresponding Cartan subgroup is compact. Yes. And in the last case, the Cartan involution is acting by the long element of the vowel group, which is to say -1, and so the corresponding real Cartan is split.
Okay.
All right?
Yeah.
And, excuse me, there's a... how do I? There's a KGB order. Oh, I think it's print maybe. Print. Oh. I'm sorry. Never mind. That command's not available here. All right. So, So that's KGB, and that plays an important role here. So probably you've looked at the block of the trivial representation?
Yes.
So let's set B is equal to a block. Actually, let's start by saying, let's set T is equal to trivial of G. Okay, so T is a parameter. All right, so this is important information. So every parameter is given by a triple.
Okay,
and,
this is what I'm very interested in.
Right. So
okay.
the first element is one of these elements from the KGB list, in this case, the element number 2.
Okay, so this is the second guy on that KGB list. Okay.
Yeah, third guy, actually, but yeah.
Sorry, third one, right, because it starts at 0. Yeah. All right.
And then the second one is a rational vector, and then the second two are rational vectors of size the rank of the group, and it's essentially true that what these are telling you is a character of this Cartan subgroup. Lambda is telling you the whoops, sorry about that. Lambda is telling you the character on the compact part, and nu is telling you the character on the split part.
Okay.
Okay, and that's literally true up to a row shift. So as you well know, we really should be talking about the row cover of this carton.
Yeah.
But since this group is simply connected, we don't have to worry about that. So
That's okay. Yeah.
So let me take a time out here.
Okay.
You see this thing, equivalence of Atlas parameters?
Yes.
Okay, so this file is on the Atlas website under the papers section.
Oh, okay.
And
Papers.
it has a very nice, concise statement of what these parameters are, and on the very first page. So let's look
That's
at it.
great.
So it says
That's
x.
exactly what we want.
So x is a KGB element, list given by an integer 1 through n. And this lambda is an element of x upper star plus rho. And it's really only defined modulo this 1 minus theta x subgroup. And every KGB element gives, here it says, of course, theta x is the carton involution defined by x. So that's one important point about these KGB elements. Every time you have an x, that gives you an involution of the carton subgroup.
Okay.
And that's varying. So if you're on the compact carton and the split carton, that theta x is going to be different.
Okay.
And then nu is an element of this space, and this is just what's known as A star. It's the minus theta invariance. This x upper star tensor Q is the rational the rational vector space, the dual of A.
Okay.
You know, H is equal to TA, and there's this vector space A, which is a vector group, and we're doing everything over Q. So this is the dual of it, and well, sorry, that's what the upper theta does. This x upper star tensored with Q is the dual of H, and then when you take the minus theta invariance, this is the dual of A. Okay.
Okay. Yeah. Yeah.
And okay, so then there's some other information here. So, for example, the infinitesimal character is always given by this formula, 1 plus theta x lambda plus 1 minus theta x nu. And that's, of course, always useful thing to keep in mind. And then there are various other technical conditions which I'm not going to worry about right now, but let me just show you. There's the standard condition and final and non-zero and blah, blah, blah. And then a careful statement of what this means. The bottom line is that if you have a standard parameter, you get associated to it as a standard module, and that's an induced from limit of discrete series. And the way we've set things up is that it has a unique irreducible quotient J.
Okay.
Alrighty? All right.
So can we just scroll up a little bit again to the top?
Yep.
Just want to get a rough feel for how these parameters mesh with my usual understanding of a standard representation.
Sure.
So the lambda is, I'm thinking, the weight of the discrete series representation on some Levy subgroup.
Absolutely.
The nu is the sort of
the A parameter.
Yeah, the twisting part.
Absolutely.
And the x is giving me some kind of components information.
No, so that's not quite right. So x is just telling you which carton. The main thing it's telling you is which carton subgroup you're on.
Oh, right. Yeah, which translates to which Levy subgroup I'm in.
Right, and that tells you the Levy, exactly.
Okay.
So the information about the the discrete series, that includes the disconnectedness in it.
And that's in part 2.
And so that's in lambda.
Okay.
So lambda tells you is all of this tells you all of that, and nu is just the parameter on this vector part.
Okay. Okay. Yep.
All right. So let's check. So we have this parameter. Whoops, I didn't set p is equal to it. So t. Sorry.
Okay. So can I interrupt for a moment?
Sure.
So now that we've got this rough dictionary between the usual picture, I see that x equals 2. Telling me I'm inducing from the split torus, right? And then the lambda is the compact part. So this should be trivial, this lambda, I guess. No?
Yeah, well, so there's always the question of row shifts. And let me come back to that in 1 second. So,
okay.
Well, yeah. So the point is we're inducing from the split Cartan.
Yes.
And so this m is plus or minus 1.
So can you say that again? It didn't come in through.
Sorry, we're inducing from the split Cartan.
Yes.
So m is plus or minus 1.
Okay.
And so it's either the trivial or the sign on that.
Oh, I
group.
see, and that's what the lambda's recording.
Right. And remember, I said that lambda, actually, let me just finish this. So here's the infinitesimal character, which is 1. And I'm just going to type something on the screen here. Remember, lambda is defined modulo 1 minus theta z to the n, which in this case is z. And theta's minus 1, which is to say 2z.
Yeah.
So now there's a question of row shift. When you induce this representation, it's either going to be trivial or sign on the SL2, and I hate to say which because I always get it wrong.
Okay. But in this case, then the lambda equals 1 is telling us that it's going to be
it's specifying
trivial component group.
Well,
right?
It's specifying the value on the component group. If it was literally 1, that would be saying it's non-trivial.
But it's not literally 1, right?
But there's some row shift, so I'm not sure.
Some funny business. Okay.
All right.
And then the new then coincides with the infinitesimal character.
Right.
Okay.
That's correct.
All right, good.
So let's just do a little experiment. Let's set P is equal to parameter. And the way you define a parameter is you specify the KGB element, in this case 2.
Okay.
And let's specify lambda, and let's specify nu. So this is the parameter I just defined. I'm just showing you could define it by hand.
Nice. Okay.
Okay. And for convenience, let's set x is equal to KGB, the second KGB element. So with that, I could say x, right? And let's check t is equal to x. Whoops. What's t?
Yeah, what's t?
Oh, I'm sorry. T is equal to x. I'm sorry. T is equal to p is true.
All right. Okay. Yeah. Okay. Good.
Okay. So now the experiment I wanted to do was to let's take the other parameter instead of 1. Let's use 0.
Yeah, that's what I was hoping you to do.
Good. All right. Good. And so here's t and here's p, and you see it changed the 0 to 2, but that's fine because it's defined modulo 2. Yeah. And one way to tell that these two representations are different is to look at their blocks. So if we look at the block of t, we see it has 3 representations in it.
Okay.
And I'll come back and say a little more about those in a minute, but if you look at the block of p, it just has a single representation in it. Okay. So what this is telling you, if you have a block with just a single representation, it tells you the way you get the block is you take that parameter, you take the corresponding standard module, you decompose it into irreducibles, you take all of those standard modules, and you keep going.
Yeah.
Well, you didn't get anywhere, so what that's saying is that this guy is irreducible.
Yeah.
And now another thing that you can do that's extremely helpful is you can load the K-types stuff.
Okay.
And so now you can say, let's look at the highest weights of the lowest K-types. Sorry, the highest weights of the lowest K-types of T is 0. That's the trivial representation.
Okay.
On the other hand, the lowest K-type of the highest weights of P are 1 and minus 1. So this is the irreducible odd principal series at rho.
Yeah. Okay.
All right.
Good.
All right, so now let's go back and look at the um, at this block. So this is the representation that we started with. So it's here's the x is equal to 2. The lambda is equal to rho plus 0, which is to say rho, and the nu is equal to 1. And what this is saying is that in this block there are two other representations labeled 0 and 1. And these are closed orbits. Also, if you look here, the root is I stands for imaginary. So these have to do with the compact Cartan. So these two representations are the two discrete series.
Okay. Now, how can I distinguish between the two of the discrete series? So, like, I'd like to find the one that's positive with respect to the roots that is positive.
All right, that's a subtle question. And as you know, in this business, distinguishing the two, there's an automorphism of the group which interchanges them. So it's definitely a little subtle, and let's look at that. So let's let I forget, did I define B? No. So let's set B is the block of the trivial representation. And let's set discrete series 1 is equal to the 0th element of that block. So there it is. Now, of course, its infinitesimal character is rho. And let's find out its the highest weights of its lowest k-types. 2. Okay?
Okay.
So this must be the holomorphic discrete series.
Right, because it's 2. And
2 and not minus 2.
The other one...
Well, okay, so now we're going to get into trouble. So I'll show you the trouble that we're in. Let's set ds2 is equal to b bracket 1. So let's look at ds1 and ds2 now. They have the same lambda and the same nu. The only difference is the x.
Yes.
Now, I told you that the main thing x does is it tells you the Cartan, but it tells you one other crucial bit of information, which is it tells you an imaginary vial chamber.
Okay.
And so these two are both on the compact Cartan, but they're in different imaginary vial chambers.
Right, okay.
And so one of them is the holomorphic discrete series, and the other one is the anti-holomorphic discrete series. But if you do lowest k-type, highest weights of ds2, you get a disturbing answer. You also get 2.
Okay.
And the reason is that this x is varying. So in the Atlas world view, a group x determines the real form, and these two x's are different. So what's going on here is that there are two different k's, two different maximal compacts here, and they're moving, and that's confusing the issue. So what you want to do is you want to fix k and define it to be the k. Oops. Oh, sorry. Set x is equal to kgb g0. I want to take this to be my basic kgb element, and I want to relate everything back to this. So I'm going to set k to be the k defined by this x. Okay?
Okay.
So k is what? K is a connected blah, blah, blah. This is a torus, U1. All right? Now, if I do lowest k-type highest weights of ds1 with respect to x, I get 2. But if I do ds2 with respect to x, that's how I see the minus 2.
Okay.
So...
All right, it takes a bit of work.
Yep. There's always some sort of conjugating everything back to a fixed x that goes on.
Okay. You mentioned something about an order in the KGB elements.
Yes.
Is there something to do with that order and knowing which which discrete series? So what I'm trying to say is the K's x0 initial was the first one, and that's the one that gave us the holomorphic discrete series.
Yes.
And then the x1 gave us the anti-holomorphic discrete series.
Yes.
Is that a coincidence that the order that the KGB orbits are appearing coincides with the holomorphic anti-holomorphic?
Oh, I see what you're saying. Yes and no. So when you say order, you mean just the numbering?
Yes, the numbering.
Yeah. Let's go to a slightly larger example so I can say something about that.
Okay.
Let's set G is equal to SP4R.
Okay.
Okay, let's look at row of G. That's good. Let's look at the simple roots of G. 1, -1, and 0, 2. So this is the usual coordinates.
Okay.
Let's print the block of the trivial representation of G. All right. So this block has 12 elements. And the x's are listed here 0 through 10. And the easiest thing to tell about a representation is to look at the status of the two simple roots. Both of these simple roots are imaginary.
Okay.
So this is a discrete series. These first 4 are discrete series.
It's all imaginary.
Right.
Okay.
And then you get some mixed stuff, and then up at the other end, you have 2 principal series. But let's just look at the discrete series. Now, notice, so I1 or I2 means that root is imaginary non-compact, and IC means that it's compact.
Okay.
And so these 4 discrete series are a little bit different. 2 of them are large, which is to say all of the simple roots are non-compact. And then the other 2, number 2 and 3, are the holomorphic and anti-holomorphic discrete series because there's a compact root.
Okay.
So the numbering, if your group has discrete series, the numbering is always, such that the very first guy, if the group is quasi-split, is the large discrete series.
Okay, yeah.
So it's sort of the opposite of what you're asking, and then the holomorphic guys tend to appear further down the list.
Okay. All right. Could we do PSP for? I'm just curious.
Sure. So now there are only 2 discrete series. And so, they get glued together, as you know. And now if you look at the other end of the output, you see something interesting, which is right here. Sorry, not those 2. 8 and 10. In 8, both of the roots are type R2, as is the case in 10. And what that means is that that's telling you the talin variant. Both of the simple roots are in the talin variant, which is telling you that representations 8 and 10 are both one-dimensional.
Okay.
And
yeah, I don't know anything about the talin variant.
Okay.
Seems like an important one.
Yeah, it's definitely an important aspect of all this. I'll just tell you that for the let's see. Let me do for P in block of trivial G. Oops. So, by definition, the talin variant is a subset of the simple roots. And roughly speaking, large representations have small talin variant and vice versa. And so here you see each one of these is a subset of 0 and 1. And this very first representation is the generic discrete series. It has empty tau invariants.
Okay.
And then down at the other end, these two representations are the smallest. Those are the trivial and the sign. And anyway, so let's see what else. So this group has two one-dimensional representations. It's disconnected.
Okay.
Yes.
So if we go back to the block just above this stuff.
This block here?
Yeah, that block there.
Uh-huh.
If I would want to convert this information into inducing from some sort of Levy subgroup,
yes,
I have to know what X is doing, right?
Yeah, so there's actually a nice command in the software for doing this now, and so let me show you that.
Great.
Well, let's start with, let's set P to be the trivial of G. And just sort of by hand, you can see, let's set X is equal to X of P. And so, by the way, you can also say lambda of P and nu of P to extract those terms. X is this KGB element, number 6.
Okay.
And the involution of it is minus the identity, so it's easy to tell in this case that it's the split carton. And
yes.
You can also construct the carton class of X, I think. Let's set C is carton class number 3. I think there's a print carton info. Yeah, so this tells you about the carton. It says that as an algebraic torus, it has no compact factors, no complex factors, and 2 split factors.
Okay.
So it's R cross squared. There's some technical information here about involutions and so on. And it has no imaginary roots, and the real roots are of type C2. So that goes a long way towards, describing it.
Yeah, that completely describes it. But if there's some sort of intermediate carton subgroup,
sure.
Let's say one real root.
Yeah, let's take a look at one of those.
Tell which one it is.
Right. So let's set P is equal to B bracket 5, maybe. Or what is B? No. So let's set B as the block of the trivial of G, and let's set P is equal to B bracket 5. Okay, so this is an intermediate guy. X is equal to 4. So let's set X is equal to X of P. And let's look at the involution of X. So clearly this is some intermediate guy.
Okay.
Yeah.
What's this involution?
Yes.
It says value. What is this?
This is a 2x2 matrix giving you the action of the carton on the on X upper star of T.
Okay.
And so, for example, if you look at the positive roots of G, there they are. And if you look at the involution of X acting on them, there they are. So what does it do? It switches this first root to minus this root. It fixes this root. And so on.
All right. Yeah, this is good. This actually allows us to say exactly what it is. Once we figure out what the long and the short roots are, the involution is pretty clear from there. I think I can do it.
Right.
All right.
So, but there's something much better, which is the following. Let's set M is equal to M of X.
Oh, is this going to give me the Levy?
There you go. M is a disconnected split real group with Lie algebra SL2 GL1.
Oh, so I don't have to do any thinking. I could just type this in.
No, trust me. Trust me. There's plenty of thinking left to do. So there, it tells you it's not. Since it's disconnected, it's telling you this is the SL2 cross R cross carton Levy, not the GL2 Levy.
Yeah. Yeah, that's right.
Okay, so let's for x in KGB of G do. Okay, so there we see KGB elements 0 and 1. The corresponding levy, of course, is all of G.
Yeah.
And then, oh, we're in PSP4.
Yeah.
Things are funny here. Yeah, this is tricky.
1G01. Okay, that makes sense.
Yeah, they're all disconnected. These it's funny. These two cartons, which in SP4 look different, in PSP4 are isomorphic. It's a little weird. So let's do it in SP4. Let's not get bogged down in that. Let's say G is equal to SP for R, and let's do it there. Yeah, this is clearer. So there are 4 KGB elements which coming from the compact carton, and then disconnected. Oh wait, I'm sorry, I misspoke. Oh no, I'm sorry, I was being silly. GL2, GL2R.
It's the same thing, yeah.
Yeah, they're both disconnected. How do you tell the difference?
We could go back to the thing you had before with the carton class. Is that what you typed?
Yeah.
Would that do it for us?
Yes. So let's do all right, that's a little bit kind of a lot of output, but let's see if we can scroll back and see.
Pick one of them.
Yeah, so let's go to whoops. Let's go to KGB element number 5 here. So, well, let's see. The first one that's not on the compact carton is this one right here. It says that the carton is S1 cross R cross. And so the same is true for 5. And the same is true for 6. But I think when you get to 7 or 8 or something, yeah, there's 8. KGB element number 8. Whoops, I'm sorry. Ugh, sorry, that was a mistake. KGB element number 8, you see the carton has a complex factor.
I see.
So this is the GL2 carton.
And that will distinguish it from the
yes.
SL2 cross GL1.
Right. Now, another thing you can do, I mean, this is actually, there's various ways to tell this. For example, if you do, if you look at this, P, I guess? Sorry, not even P. Trivial of G, that's what I want. So here's this block again. This, where is the information? This number here is in this column is the length, and
length of what?
The length of the parameter. There's a notion of length of a Harshchandra parameter.
Okay.
And well, okay. I guess. Yeah. Anyway. So another thing that this tells you. So these this column here is giving you the cross action. And these two columns here are giving you Cayley transforms. I don't know, are you familiar with these concepts?
A little bit, yeah. We talked about this when I came to visit you. Yeah.
Okay, so...
is it written up somewhere on the website?
Yeah, I mean, I think the algorithms paper is probably a good place to look. Now, that is more mathematical and not so close to the software, but anyway, it's explained there. The what you see, for example, is that the first thing to observe is that these not the Cayley transform, these cross actions always move you around on the same carton. So these 4 guys are all living on the compact carton. And
remember correctly, that's the complex vowel group acting on the representations, right?
Yes,
Cross-section. Okay.
that's correct.
Yeah.
And so you see, for example, the representation 4 and 7 and 5 and 8 are all on the same carton, whereas 6 and 9 are on this other carton. So 6 and 9 are the GL2 carton.
Let's see.
Because you can go by a cross action from 6 to 9 and 9 to 6, but nowhere else.
I see.
And then these Cayley transforms take you up and down to different cartons. So, for example, representation 0 is on the compact carton. If you do a Cayley transform, you get to representation 6, which is on some other carton.
Okay.
And basically, these two operations, Cayley transforms and cross actions, fill out the block. If you start with any single representation and apply Cayley transforms and cross actions to it, you can move around the entire block. And everything you need to know about the quasi-journalistic algorithm and the structure of the block and principal series and all that stuff is captured by those 4 columns.
That also tells you about the carton subgroup that you're moving to, if you know what the Cayley transform is, right?
Absolutely. Yep. Yeah. So, for example, if you this first root is short, and the second root, symbol root, is long, and so this carton number 6 is the so-called short root carton, and this carton 4 and 5, the 4 and 5 are the long root carton.
Okay.
All right.
Okay. Good. Well, at least we know where to look to get an idea of what's going on. All right. So the next thing I'm wondering about is, I guess you touched on this in your introductory video about how to decompose induced representations or standard representations into irreducibles.
Right.
And then also get the character formula of an irreducible representation in terms of standard representation.
You bet.
Has anything changed there? Is it the same as in that introductory video?
Probably. There's a few. That video is a little old, and there may be 1 or 2 small things, but it's very probably, as far as that goes, not. Should we do a couple examples?
Yeah, sure.
Let's go back to SL2. That's the only group I really understand.
Yeah, that's good.
Let's set P to be the trivial of G. Okay. So now, one of the confusing things about the software is that a parameter can stand for either an irreducible representation or a standard module. And now I'm actually working on something now which is going to have some new notation where you'll be able to say I of P and J of P to distinguish between irreducibles and standards.
I thought you already did that.
Well, I did, but it got lost. It's no longer in the. It hasn't been migrated to the newest version of the software. So you're right. Where you saw that in the module stuff?
Yeah, I did.
Yeah. Okay. So I have to sort of reincorporate that. So it's not here at the moment.
Okay.
In any event, yeah. Go ahead.
Yeah. How do we get the standard representation?
Yeah. So if you ask for composition series is telling you the irreducible quotients of a standard module, and so you just say P, and by definition it says, okay, I'll tell you what the composition factors of this standard module are, and it's going to give us a list of parameters. And so it says that the standard module I of P is the sum of these 3 irreducibles.
Okay.
And so this is saying that the spherical principal series of SL2 at rho decomposes into the sum of the 2 discrete series plus the trivial representation.
Okay. I'm curious. Again, the order that these are listed in corresponds to the numerical order in the KGB orbit.
Yes.
Is that always going to be the case?
Yes.
Okay.
Yeah.
Okay.
Now,
Well, it's important if
I mean, there could
say I
be
want to write out a matrix or something to change back and
yes.
forth between.
Yeah. Now, I mean, there could be multiple multiple guys with the same KGB element. So, for example, up here in the block, both these guys have the same guy 10. So, I'm not positive of this, but I think what you get in the output will. I wouldn't count on this.
Right.
It would be nice if the output was listed in the order of this, but I can't guarantee that.
Okay. Okay. Well, we'll keep an eye out for that.
Now, by the way, there's. Let me show you a little terminology. I'm going to set capital P is equal to this thing. So P is what's called the parental. It's a polynomial of parameters, and
how is it a polynomial?
It's got these coefficients 1. It's 1 times this plus 1 times this plus 1 times that.
I see what you're saying.
Because there could be multiplicities.
Okay.
And sometimes it's a little. It might seem a little confusing. If you just want the irreducibles in this list, you can say set constituents equals monomials of capital P. And that just gives you the list of the 3 parameters. So if you want to do something with them, that's the way to get access to them.
Okay.
Now, the inverse is the command character formula of P. So what this says is, since I asked for character formula, you must be talking about the irreducible representation J of P, which is the trivial. Please write it as a formal linear combination of standard modules.
Yes.
Well, it's the original standard module right here minus the 2 discrete series.
Okay. All right. Now, I remember, I think in the modules video, you also had something called virtual.
Is that here? I'd forgotten about this. What? Oh yeah, virtual doesn't do much. Virtual just says if P is a parameter, virtual of P is the corresponding polynomial 1 times that parameter.
Okay.
That's all.
Okay. Yeah, what I'd like to do is work in the Grothendieck group of the irreducible representations. And it seemed to me that this virtual business was going to help me do that. It was somehow a way of distinguishing between a representation and the character of representation.
Well, it's not virtual exactly. I mean, it's really the crucial thing is this parental notion.
Okay.
So, so let's do an example. Let's see, what's a good example?
So can I add 2 parentals, for instance?
Of course.
Yeah. Okay. Okay.
And you can add. I think you can add a P to a P. There you go. Yeah. So it's yeah. I mean, this really is the world of parentals is exactly the Grothendieck group.
Okay, that's terrific. So in that expression that you just typed in, the capital P, let's see, that's the sum of what? Well, what was it again? Capital P?
Yeah, so capital P is the sum of these 3 parameters.
Okay.
And now again, even with parentals, you need to be careful if you're thinking of it as a sum of irreducibles or as a sum of standards. Here we're thinking of it as a sum of irreducibles. Right. In any event, you can. So really, a parental it's the Grothendieck group of parameters. an element of a parental is just a formal linear combination with z coefficients of the parameters.
And is it safe to interpret those parameters as the irreducible representation, the line length quotient?
Yes.
Okay.
As long as you are careful when you apply a function to it, because some functions are expecting, standard modules, and you won't get an error, but you'll get confused.
Okay.
You might get the wrong answer.
Okay.
So, for example, let's take P. Let's take the composition series of P. And let's take the character formula of that. All right, let's think about what that does. So P is a standard module.
Okay.
Composition series says, please write that as a sum of irreducibles.
Yes.
Okay, now take that sum of irreducibles and please write it as a formal linear combination of standard modules. In other words, composition series applies perfectly well to a character formula applies perfectly well to a parental.
Okay.
So these two operations are each other's inverses.
Right.
Pretty cool, huh?
Okay, yeah, it's great.
And you can
do
it in the other direction. Composition series of character formula of P is equal to P. Okay?
Okay. Yeah, well, if you get the I of P and J of P up and running, it'll be a little bit easier on the brain.
I agree. I definitely agree.
But in the meanwhile, we'll have to make do with this. Okay.